Hello, Dr. Shahab. My name is Karim Jmail, and today I will be discussing MIPS, every overflow in MIPS, multiplication, and floating points, everything related to MIPS. So, how to deal with overflow in MIPS? In MIPS, overflow is dealt with an exception. An exception is usually like a small problem that what isn't expected to happen. It is also called an interrupt, and uh, and when this exception happens, the instruction where it happened is stored in something called the EPC, the exception program counter. And in this EPC, the instruction is stored in order if we want to resolve this exception, if we want to solve it in some way, we can, and then go back to this EPC and continue the execution of the instructions from where we stopped. Now, overflow is dealt with in the same way with this exception. However, MIPS does not have an implicit program that can resolve overflow. The user should write his own MIPS code in order to do so. Okay, so here we have the overflow code. It's a simple code. You take two signed integers, and if you add them, unsigned, of course, and depending on the result, you would know if there is an overflow or not. Let us just take a simple example in order to demonstrate this. First, we will try to add -7 with -6. This usually will cause an overflow if you are using just 4 bits or even more. Let us start. If we add them unsigned, we will get a result of 0, 0, 1, 1 with a carry of 1, which is the overflow. In this case, we will XOR the operands and we will get a result which is greater than 0. After that, we will move to the set less than instruction, and we will see that T3 will be greater than 0 and not less than. So T3 will be set to 0. Now, since 0 is equal to 0, so this will state that there is an overflow, and then we move on to the next instruction, which is the XOR instruction, the second XOR instruction, and we will XOR the result of the addition with the first operand. In this case, we will get a result which is less than 0. We'll get 1, 0, 1, 0, which is less than 0, and the set less than instruction will be executed and T3 will be set to 1. Now for the last instruction, since 1 and 0 are not equal, so this program will branch to another code which will deal with this overflow. Now in MIPS, we have also multiplication. This multiplication will take two 32-bit numbers and put the result will be a 64-bit number. Now this 64-bit number is divided into two parts, the high part and the low part. The most significant 32 bits are stored in the high part, and the least significant 32 bits are stored in the low part. Now, let us just take a simple example in order to demonstrate this. First, we will multiply 4 and 3. So we'll load 4 into A0 and load 3 into A1. Then we will multiply them. Now, for the MFHI, which is move from high, we'll move everything, all the result that was placed in high into A2. In this case, it will be full of zeros because 4 times 3 is 12 and can be fit in 32 bits. So all of the result will be stored in the low part of the multiplication. So in the last instruction, we will move from low and into V0, which is our result. MIPS division is very similar to MIPS multiplication, but the only difference is that the 32-bit, the most significant 32 bits are stored in high are the remainder of the division, and the least significant 32 bits represent the quotient and are stored in low, of course. So let us just take a simple example in order to show this. First, we'll load 6 and 4 into T0 and T1 respectively. then we will divide them, and then when we do 6 divided by 4 will have a quotient equal to 1 and a remainder equal to 2. So in the high we will have 2, which is the remainder, and in the low we would have 1, which is the quotient, but they will also be represented in 32 bits. So now we will discuss floating point in MIPS. MIPS has two coprocessors, coprocessor 1 and coprocessor 0. Everything regarding coprocessor 1 deals with floating points. Everything regarding coprocessor 0 deals with integers. So now we will be dealing in coprocessor 1. We know that there are 32 floating point registers that are numbered from F0 till F31, and we can pair these registers together on condition that they are even registers in order to create double precision registers. So we are allowed to pair F0 with F1, but we are not allowed to pair F1 with F2, and so on. Now, the regular arithmetic operations that we perform in integer MIPS cannot be performed in floating point MIPS. So the floating points in MIPS have different and unique operations that need to be performed on. Now this is a list of the operations that can be performed in MIPS, in floating point MIPS, and they are divided between single precision and double precision, and they are just very similar operations as if we are dealing with integers. Okay, so let us just take a simple example which will transform from kilometers per hour to miles per hour in order to understand. First, we need to know the formula, which is you take the value you have in kilometers per hour and you multiply it by 0.6213711, which is a very long integer. We'll just take the four first digits for simplicity. Now this constant is stored in the global pointer, which has a result placed for it. So let us say that our argument, which is the kilometers per hour, is an integer. First, we'll load it into T1. Then we will take this and take it to coprocessor 1, which is the MTC1 instruction, and there it will remain an integer form. It is just in coprocessor 1. Then we need to convert it to a double, which is from integer to double, and we will store it in F2. Then we will load our constant from the global pointer, and then we will multiply our constant with our argument, which is already in form of floating point, and the result will be stored in F8.